In reinforcement learning, the success of an autonomous agent hinges on one critical factor: the reward signal. This signal acts as the compass guiding the agent through its environment, shaping behavior toward desired outcomes. Yet designing effective rewards, especially for complex reasoning tasks, remains a persistent bottleneck. Manual reward engineering is fragile, prone to reward hacking, where agents exploit loopholes to maximize scores without achieving the true goal. And when rewards are sparse, like a simple binary success failure flag, learning over long horizons becomes inefficient and unstable. Traditional approaches have leaned on human-in-the-loop systems like reinforcement learning from human feedback, RLHF, where expensive annotations train dense reward models. But as Sutton's The Bitter Lesson reminds us, strategies reliant on human priors are ultimately less scalable than those that leverage computation to learn from experience. To break free from this trade-off, researchers have turned to automated reward optimization, using evolutionary algorithms to evolve reward functions via mutation and selection. But these methods are fundamentally blind. They treat the reward function as a black box, relying on stochastic perturbations without capturing the causal relationship between reward structure and task performance. As a result, they're sample inefficient and struggle to scale. What if we could make this process differentiable? What if the meta-optimizer, the entity evolving the reward, could learn not just what reward works, but why it works by approximating the gradient of task success? Enter differentiable evolutionary reinforcement learning, DERL, a bi-level framework that transforms reward design into a gradient-guided, closed-loop optimization process. At its core, DERL features two intertwined loops. The inner loop, a policy model, evolves based on a dynamically generated meta-reward. The outer loop, a meta-optimizer trained via reinforcement learning, generates new reward configurations, using the validation performance of the inner policy as a feedback signal. Crucially, unlike traditional evolutionary methods, DERL is fully differentiable. The meta-optimizer isn't just mutating random strings, it's learning to generate reward structures that maximize downstream performance. It's learning the meta-gradient, the sensitivity of task success to changes in the reward function. This is where the real innovation lies. Instead of generating arbitrary text, the meta-optimizer composes reward functions from atomic primitives, modular, executable functions like format checkers, partial goal verifiers, or step count heuristics. These primitives are easy to obtain, logically interpretable, and serve as building blocks for complex evaluation criteria. The reward function is then defined as a symbolic composition. R /phi OC /text func G1 OC /dots GK OC /phi. Where /phi dollar represents weights and operators, like sums, products, or logical conditions, that combine the outputs of the primitives. This design ensures a structured, expressive search space, rich enough to capture nuanced feedback, yet constrained enough to avoid the chaos of free-form text generation. Now, how does the meta-optimizer learn? It uses the validation performance of the inner loop policy, not just as a score, but as a supervisory signal. After training the policy under a given meta-reward, we evaluate its performance on a held-out set. That score becomes the outer loop reward, which the meta-optimizer maximizes via policy gradients. This creates a closed-loop computation graph. The final validation performance flows backward through the reward function, the policy, and into the meta-optimizer's parameters. The system learns to generate denser, more actionable feedback signals, not by guesswork, but by gradient ascent on task success. We validate DERL across 3 domains. 1. Robotic agents in ALFWorld, where agents must complete embodied household tasks using natural language. 2. Scientific simulation in ScienceWorld, testing reasoning over elementary science concepts. 3. Mathematical reasoning on GSM 8K and math, ranging from grade school arithmetic to competition-level problems. On all benchmarks, DERL achieves state-of-the-art performance, outperforming not only outcome-based rewards, but also complex heuristic combinations and prior state-of-the-art methods like RLVMR. But the most striking results appear in out-of-distribution, OOD, scenarios where training and test data come from different distributions. Standard baselines, even those with better in-distribution performance, collapse under distribution shift. GRPO with average rewards improves on L0, but gains only 0.8% on L2. In contrast, DERL more than doubles the outcome reward baseline, achieving 65% success on ALFWorld L2 and 30.1% on ScienceWorld L2. Why? Because DERL doesn't overfit to specific examples. It discovers the intrinsic structure of the task, learning to reward correct reasoning, not just correct answers. Our analysis reveals a fascinating evolutionary trajectory. Early on, the meta-optimizer explores unstable reward structures, unbounded products, negative coefficients, or volatile chains that vanish when any signal is 0. But as training progresses, these disappear. Stable structures, linear combinations, normalized terms, bounded operations, dominate. The system implicitly learns that numerical robustness is essential for reliable optimization. This isn't random search. It's natural selection at the level of reward functions. The meta-optimizer evolves not just better rewards, but better ways to design rewards. We also compare DERL with a population-based variant, DERL-pop. Here, instead of reinitializing the policy from scratch each time, we carry forward the best-performing model from the previous generation. This creates a curriculum-like effect, accelerating convergence and boosting performance. On ALFWorld L0, DERL-pop reaches 91.8% success, and on ScienceWorld L0, 98.2%, nearly perfect performance. In mathematical reasoning, where outcome rewards are already strong, DERL still shines. Naive combinations of format and outcome rewards degrade performance on math, likely due to reward hacking or distraction. But DERL discovers non-trivial compositions that boost accuracy to 60.2% on math, outperforming even the outcome reward baseline. And in the long run, DERL converges smoothly. Training dynamics show a consistent, monotonic increase in both training and validation performance. No overfitting, just steady improvement. The meta-optimizer learns to generate meta-rewards that generalize, adapt, and self-improve. This work marks a paradigm shift. DERL moves beyond black-box evolutionary search. It transforms reward design into a differentiable, gradient-based optimization problem, enabling autonomous discovery of reward signals without human annotation. It's not just a tool, it's a self-improving framework where the system learns to learn better objectives. It captures the meta-gradient that human experts intuitively use when tuning systems, the sense that tweaking a reward parameter will shift behavior in a predictable way. Of course, challenges remain. The computational cost is high. Each outer loop update requires training multiple inner policies. But solutions exist. Lightweight proxy tasks, more efficient outer loop algorithms like Reinforce++, or population-based strategies that reduce redundancy. And while the expressivity of the reward is currently bounded by the atomic primitives, future work could explore automatic extraction of new primitives from task descriptions, opening the door to even richer reward structures. In conclusion, DERL isn't just another RL algorithm. It's a step toward truly autonomous agents, systems that don't just follow instructions, but discover what it means to succeed. By enabling the meta-optimizer to learn the gradient of success, DERL closes the loop between reward and performance, turning reward design from a bottleneck into a self-optimizing engine. The future of reinforcement learning isn't just smarter policies. It's smarter objectives, designed not by humans, but by machines learning from their own mistakes, guided by the signal of success itself. And that, perhaps, is the true power of differentiable evolutionary reinforcement learning.